All right, so just double checking. You guys still see my screen, right? All right, good. So let's kick start. So we're gonna look at matrices today. So real quick. So, we're mostly stick to the notes, and if there's any pressing work, we just work it on the other screen. So you guys should be familiar with matrices somewhat. So what we have here, we have matrices, addition and subtraction, multiplication, inverse matrices, solving linear equations. So you can find the inverse of the matrix, and it's supposed to help you to solve simultaneous equations really. Um, and then you have the transformations that you can use with matrices. All right, so matrices, addition and subtraction. So basically, so I want to read from it and give my input where I see necessary. The numbers shown in a matrix can be in many different shapes and sizes. Right? And I give the examples. So we have a matrix like that, one like that. So you get the vibe that you have, a rectangle, you have some numbers in there, some elements, I guess I can call them numbers arranged in different ways. So I have this look like a square, this one, and they have this horizontal, um, and I give it the official names later though. You have this vertical looking one, and then you have this other one that has more rows of numbers than columns, right? So you have 3 rows, 2 columns. So we describe these shapes and sizes by giving the dimension of the matrix. Notice the bold, dimension in bold, right? So the dimension is number of rows in the matrix by number of columns. So going back to this one, so this one has 3 rows, 2 columns. This one right here has 1 column, 2 rows. So even though you kind of look at this is, when you count it from top to bottom, count 5 and 3, top row, bottom row, 2 rows where you have 1 column coming down. And this now you have 1 row where you have 3 columns. And then this now you have 2 rows, 2 columns, right? So it's a rows are along the horizontal, columns are vertical. Then it asks, what is the dimension of each of the matrices shown above? And we went through them before, 2 by 2, 1 by 3. This is 2 by 1, and this is 3 by 2, right? Again, we'll count the number of rows first, then you count the number of columns. So in general, if a matrix has m rows and n columns, its dimension is m by n, number of rows by number of columns. We often write this as m times n, right? But the multiplication sign does not mean multiply, it just means by. Then it says you can add and subtract matrices by adding and subtracting their corresponding elements. Matrices have to have the same dimensions in order to be added or subtracted. So going back again, same dimension just mean number of rows, same number of rows, same number of columns. So if you look here, in order, if you got a question that asks you to add this matrix to another, then the other matrix would have to have, or would have to be arranged in such a way that it have the same number of rows, which in this case is 2, the same number of columns, which in this case is also 2. So that's what it's saying. If you choose another one, if you were to add this matrix to another, you would have to have 2 rows and 1 column. So you could think of maybe say 6 and 9, you know, um, 10 and 12, whatever the case may be, but you just want to make sure it have two rows and one column. All right. Let me give examples right here. So calculate, notice that it have the same number of rows, same number of columns coming down. Yeah, and they add it up and you add element by element. So they will flesh that out and show you. So solution, you add element by element, you add 5 and 5. And when I say element by element, corresponding element. So the first, the element in the top left corner here is added to the same element in the top left corner. And the one to the right, top right, is added top right. See there? So top left and top left, top right and top right. Bottom left, bottom left, and then bottom right, bottom right. There. Yeah. So you add them up, 5 and 5, 10, -1 plus 1, 0, 2 minus 2, 0, 0 plus 5, 5. You get it, and that's it. Simple as day, right? And then for subtraction, again, element by element. So this is 4 minus 10, 3 minus 2, 1 minus 5. So notice they put the minus sign here, and then the number is -5. So you put -5 in bracket. And then we know that minus and minus is positive. So you're going to have 1 minus -5, which is actually 6. Go again, 6. 6 minus 4, and so on and so forth. And end up get this matrix here. Notice again, same number of rows, in this case, 2 rows. See there, 2 rows again, 3 columns, 3 columns. So you have to remember that you have some questions that, they say, can you add these two matrices together? And when you look at have different number of rows or different number of columns, and they're just testing if you remember this concept that they have to have the same number of rows as columns. That's all they're testing. Then right here now it gets a little interesting, because now they have some variables. So it's like, given that you have this matrix here, notice that it has a like a variable here, and this has a c, another variable, and it's saying that this subtract this matrix subtract this matrix equals some other matrix, and it's asking to find the values of these variables a, c, d, b, or I guess as I said the other way, a, b, c, d, right? So you're here now. All you do is you follow the concept above where you subtracted corresponding elements of both matrix. So look here, you have A, you have 4. So A minus 4, because asking to subtract. So A minus 4 is equal to 5. Another one, 3 minus C is equal to 0. So notice that they're listing the information that they have, right? So again, A minus 4 is equal to 5. And you can solve for that simply, right? That means A equal 9. Here you go again. 3 minus C is equal to 0. That simply means that C equal 3, right? Because 3 minus 3 is 0. And you go on, right? Minus 1 minus D is equal to 0. That means D is minus 1, right? Because minus, see there, minus minus, and this will become a plus 1, then you can have minus plus 1 equals 0. And then lastly, B minus minus 5 is equal to 5. And that means B is equal to 0, right? So that's it. You use the fact that you subtract corresponding elements, and you equate it to the corresponding result that it's supposed to have. See, A minus 4 is equal to 5, corresponding top left, top left, top left, right? And so on and so forth. Now coming down, all this is asking, is what is the dimension of each of the following matrices, right? So again, we just give the information: number of rows, two rows, two columns. Here, 3 rows, 1 column, 2 rows, 3 columns, and so on and so forth. Now we have some questions right here. It said for the matrices A 3 1 2 0, B 2 minus 1 0 minus 4, they're asking you to do some addition and subtraction now, right? And here they're asking you again to do some addition and subtraction, and they say where possible. And why they say where possible is because again, they can only add or subtract matrix with the same dimension, or matrices with the same dimensions, right? So you can only add a 2 by 2 with a 2 by 2, a 2 by 3 with a 2 by 3. So it just say, all right, add up some matrices that are given here. But it don't mean say it possible that you can actually add them. So you have to test first if you can, and then where you can't, you just don't do it. So let's see if we can find something, say A plus B. All right, so watch here. So this has 2 rows, 1 column. This has 1 row, 2 columns. Straight off, you can't add that. You can't do anything with that. And then you go through, E is what? E is 0, 0, 1. This is 2 rows, 1 column. A is 2 rows, 1 column. Excellent. We can actually work this out. And so on and so forth, right? So based on what we've been doing, I may not work this out because this is straightforward. If you follow the whole corresponding elements of the example up top, you will see that is not a big problem. All right, here's another one. Given A5 2B 4C D minus 1, so you're adding these two matrices, and this is the result. And all it's asking you to do is to find the values A, B, C, D. So again, it will be the same corresponding setup. A plus 4 is equal to 0. That means A equal minus 4. Again, let me see. 5 plus C equal to 10. That means C is equal to 5 as well, because 5 plus 5 is 10. Let me see what else. B plus minus 1 is equal to 0. That means B equal 1, because 1 minus 1 is 0. So you get the gist, right? Nothing too difficult to go through. And then again, is the same situation here. Of course, the matrix is a little bigger. You have 2 rows, 3 columns, but it's the same principle, right? So you go again, minus 2 plus A is equal to 4. And you ask yourself, based on like 6 minus 2 plus 6 is equal to 4. Yeah, and you just continue to the same corresponding thing, and you find the unknowns, just like solving a simple linear equation. Now we'll get into the more interesting section, right? The more interesting section now is matrix multiplication. But before I continue, is there any questions related to the addition and subtraction of matrices? Any questions? Going once? Going twice? Okay, sold. All right, so let's go to matrix multiplication now. There are 2 types of multiplication defined for matrices. So it's a scalar multiplication Here, each element of the matrix is multiplied by a scalar, that is a number. For example, you have 2 on the outside of this 2 by 2 matrix. And all that happens is that you use this 2 to multiply each element of the matrix. So 2 times 4, 2 times 3, see there? So 2 times 4, 2 times 3, 2 times 1, 2 times minus 1. You work all of that out and you get the final matrix, right? 8, 6, 2 minus 2. And that's really it for scalar multiplication. Just use that number on the outside of the matrix and multiply each element inside the matrix by it, right? So work example 1. If A is equal to this, and B is equal to this, then they say, what are 2A? So 2A is just to multiply each element. What's half A is just half multiply each element. And then minus 4B, minus 4 multiply each element. So you have minus 4 here, positive 4, minus 4 when you multiply. Right? So straightforward as they come. Now we get into the proper meat of the matter, I would say. It's a matrix multiplication. You can multiply 2 matrices, A and B together, and write C equal AB. Only if, now this is very important, only if the number of columns of A, right, is equal to the number of rows of B. That is, A has dimension M by N, B has dimension N by K, right? So the resulting matrix C has dimension MK. So check this out. Say if you have the matrix A with dimension M by N, matrix B have the dimensions N by K. To test if they can actually multiply, you look at the N right here and the N right here. So whatever just as it said, whatever the column number is, which is represented by the N right here, and the row number is, which is represented by this N, when they are the same numbers, then you're free to multiply. And then the resulting matrix will have a dimension M by K, right? And of course, we're gonna make this concrete because this may not make any sense there right now. So of course, I'm gonna give an example, make it more concrete. So check this out. You have this matrix, 2 rows, 2 columns. This matrix, 2 rows, 1 column. Now, following up here, it says, so we would write this thing and say, this is 2 by 2. All right. What about here? This is 2 by 1. No, we say that, to explain everything right here. So we say that the number of columns, right, in matrix A, which is 2, matches the number of rows in matrix B, which is also 2. So we know that they can multiply. You know, it is possible to do the matrix multiplication without any problem. Now the question, another question is, what will the resulting matrix look like? Well, it has, the resulting matrix may have 2 rows, right, and 1 column. And it just stems from this, right, up top. So let's check. First, check the dimensions. A is 2 by 2, B is 2 by 1. So C equal AB is defined. That means you can actually do this matrix multiplication, right? Just as we mentioned before. And then the resulting matrix is a 2 by 1 matrix, 2 rows, 1 column. Now, we need to look at how the multiplication is done. I think that is the most significant part of this. Well, of course, you have to know that the thing can actually multiply, right? After you know that, which is, a given that you have to know that, then the next thing is to know how to actually do the multiplication. Whenever I think about matrices, I always remember the number 7. Comes so, 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 so. So let's see if it applies here. So 1 minus 1 minus 1, 2. All right, let us see. So we have 1 multiplied by minus 1. So it's this one, that is being multiplied by this minus 1. So think about the 7 now. You see the 7 form out. And then minus 1 multiplied by 2. So the 7 now cross. So you do the row and then the column. See? The row, then the column. That's why I just remember 7. And I know how to multiply my elements. 1 times minus 1, minus 1 times 2. And of course, this is this times this plus minus 1 multiplied by 2. Then here's another one now. Minus 2 times minus 1 plus 3 times 2. So the 7. Of course, the 7 kind of word is like, I don't know, it's like, I guess you could call it the upside down 7. Yeah. But, just remember crossway down or crossway up. Either way. After you simplify in this, I guess you could call it this intermediate matrix where you do the calculations, simplify this, I get minus 1, simplify this, I get minus 2, so plus minus 2, here I get positive 2 plus 6, and then now you just continue simplifying. So you get minus 2, minus 1, minus 2, minus 3, 2 plus 6 is 8. Call it a day. Here's another example. This is a 2 by 2 matrix, a 2 by 2 matrix. So straight out the gate, you don't have to even think. We know that the column number here matches a row number here. Right? No problem. So we just need to apply our, the method of multiplying. So 2 times minus 1 plus 1 times 5, form up a 7. So you get this piece here. Right? Not so easy to highlight. That's everything I go. But you get that piece there. Then you go again. So all right, this and this. Right? So the next thing to know with this, that is different from up top when you had one column, is that with 2 columns, you just apply 2 times. So it is 2, 1. You're going to use this 2, 1, and you're going to multiply with this minus 1 and 5. And you do it again, the 0, minus 1, and the minus 1 and 5, and you stick it under. And in a sense, it tells you, so this is telling you, okay, in the resulting matrix, put the result of me multiplying this row and this column in the top left section. Because look at this, this is top down and this is left. So put the result in the top left. Then right here, so this is bottom, this is left. Put the result in the bottom left. Over here now, this is top, this is right. Put the result in the top right. This is bottom, this is right. Put the result in the bottom right. So it tells you where to put it. So some people, they are confused, but that is how you can, that is what you can use to remember. So 2 times minus 1 plus 1 times 5. Just like that, you get your top left number. And then again, 0 times minus 1 plus minus 1 times 5. That's where you get your bottom left number. And you go again and again. And you see that it work out. After you simplify these, 2 times minus 1 is minus 2. 1 times 5 is 5. This can work out to minus 3. Then you go again. 2 times 2 is 4. This has 0 right here, so you just get 4. And then you go and go through and you get, so you get that, simplify it, get minus 3, simplify this, and you get 4, so on and so forth. All right. And then this is another example. Not new under the sun right here. Not new under the sun. All you have to do is practice, because that's the essence of matrices. It is difficult when you don't practice. You don't want to be trying to remember how to multiply a matrix when it is possible and all of these things a day before exam. It is just too much a day before. So you try and practice this thing. All right. There's a note. AB is not equal to BA. And this shows that matrix multiplication is not commutative. That is, the calculation cannot be reversed with the same result. All right? I think they had AB up top. Let me check here. So you have AB, so multiplying matrix A by B gave you this, minus 3, 4, minus 5, 0. But when you reverse this, that this is AB now, but when you multiply matrix A by B by A, right? Or whichever way you want to say it, B come first, A second, you get a different result. And it is making a point that you can't, it's not like regular multiplication where it's like, okay, 2 times 3 is 6 and 3 times 2 is 6, right? You can't just flip the numbers around and think you're going to get the same result. You're not going to get the same result. All right. So we're going through. What else we have here? We have worked example 4. But before I continue, is there any questions? Any questions? Anything so far? Going once.
Hi, good morning, sir.
Morning, Allison.
I am not really getting it like that, but I know if I practice because it's kind of confusing when you're multiplying the column and the rows across.
Mm-hmm.
Yes, but I know if I practice, I'll get it.
Okay. Yeah, it is certainly something, and I want to make sure that you guys get this thing, the multiplication, because it is something that you don't want to miss. And I don't have any problem bringing up a slide and writing this thing off. Let me see. Now there's the 1 on our own. Can probably do 2. So let me see if I can write this thing. Hold on a second. Let me see if this thing is all right. It looks like it's up. Let me use this pen. All right. So I'm going to just quickly, you can see the PowerPoint up. Just making sure. Alison, you can see my screen?
Yes, sir.
You see
Not. I'm just seeing a little box. Oh, yes. I'm seeing
it?
it.
All right. So I'll soon make it bigger. I just want to make sure I write down the matrix before.
Okay.
All right. So A is 2, 1, 0, minus 1. All right. So we have this, and we're asked to multiply it, right? AB. So 2, 1, 0. All right. And also I'm going to put this at the top. All right. So as I was saying, if you can just remember 7. Let me see how this pen look. All right. So you go here, go here. So to across and down. So this tells me that my result is going to be in the top left. So, right. So if I were to go here, maybe I need some space. No, not sure. All right. So ideally, I want to work this thing one under the other. Hopefully, I don't run into space problems, right? So 2, this I could be low. So 2 times minus 1. So this times this, and then now you're going to say plus 1 times 5. So you take care of that piece, and then you go again. This, again with this. You have 0 times minus 1, right? 0 times minus 1 plus minus 1 times 5. And you're done with the left piece of B. So you're going to multiply all this now by the right piece of B. So I'm going to now try to find a different color. So it's going to be this now. Oh, but there would have been kind of a different color highlighter. All right. I'm trying blue. All right. So this again, this time now you're going to multiply over this side. That's all right. 2 times 2 plus, so this thing here is 1. Let me kind of probably going to run into problem if I try to clean off that. Anyway, so 2 times 2 plus 1 times 0. Then again, this multiplied by this. So now you have 0 times 2 plus minus 1 times 0. All right. So hopefully everything is jiggy. So you look nice. All right, try and simplify these guys now. So it's all right. We'll have minus 2 plus 5. Right over here, this turns 0, so this is just minus 5. So this is 0, and this is minus 5. Over this side, this is 4 plus 0, and then this is 0 plus 0. And you work it out some more, simplify. Which part?
The last bracket you did there.
Okay, so all I'm doing is to simplify these up top. So 2 times minus 1 is minus 2. Plus 1 times 5 is 5. You see that? So all I'm doing is simplifying here. See the 2 times minus 1 times 5 is 5. 0 times minus 1 is 0. Minus 1 times 5 is minus 5. 2 times 2 is 4. 1 times 0 is 0. 0 times 2 is 0. Minus 1 times 0 is 0, right?
Okay, sir.
So after that, now I just, add them up. So these little piece here, so this and this, so minus 2 plus 5 is 3. Then I go to this section here, 0 minus 5 minus 5. 4 plus 0 is 4. 0 plus 0 is 0. I'll cross our finger and hope so we did it. Whenever I make any errors, that as I say, like I have to make sure that you multiply the elements correctly, you make sure you check your signs and everything is good. And hopefully everything is good. So this is 3, 4 minus 5, 0. See it here? Minus 3. But actually, I said minus 3. Same thing. So we'll get the 4 minus 5, 0. All right, let us see where we go wrong with the minus 3. Okay, so based on what I'm seeing here, the book is actually wrong. Check this out.
Yes, sir. Yes,
You
sir.
see it? You see it? All
It's
right.
where you have the minus 3, yes. The
Yeah.
minus 2 plus 5, yes.
Yeah. So they're wrong. So that's good. So we can even spot errors in books now, right? All right. So good stuff. So let me try and do. There was another one that is slightly simpler. And I think we should look at it. Let me see if I can find it. The one that was before this. This one. So we can look at this one. So this is, make it small and see. See, that's how you have to make sure you double check, because even the notes have a little mistake to show you say you have to just make sure you check. All right, so I think, so let me put this as a minus 1 1. Oh, so let me fix this here. So this is actually that, right? And then b, let me call b minus 1 2. All right, so big it up now. So the dimensions of this, I just mentioned it just to drive home the point. The dimension of matrix A is 2 times 2 or 2 by 2, meaning 2 rows and 2 columns, right? Then this now is 2 by 1, meaning 2 rows, 1 column. So to test for, I will call it, let's call it compatibility, that it can actually be multiplied. You need for the column from matrix A to be the same as the row, the number of rows of matrix B. And once that is the case, so they are the same, right? So we can tick off that, that's good. And then beforehand, we can tell you, we can know what the resulting matrix will look like. It will have 2 rows and it will have 1 column. So we'll look for a matrix that is like this, right? Element up top, element at the bottom, that's it. 2 rows, 1 column. All right. So we'll do the multiplication now. So A, B, 1, 1, minus 2, 3. So we'll say, all right, 1 times minus 1. So we're going again, like so, and so. So 1 times minus 1, then we put a plus sign, 1 times 2. Next to go, let me change the color. I'm trying to get you, man. I may actually undo so this thing look better. All right. So this, right? So -2 times -1 plus 3 times 2. So when you work out here, this is just saying 0 plus 2, 2 plus 6. And you fix that up a bit, simplify, you get 2, 8, right? So you get 2 and 8. So let us see what our thing is showing. So we have, so it look like something get missing. Let me see. First of all, let's test if we write on the right thing. All right, so we never write down the right thing. So this is supposed to be a -1 up here, right? So it's fine. We get the concept. No problem. All right, so we know what we're about. Let us see what else is there. I think what we did. Oh, so this was just the solutions to here where it says, given these matrices, determine whether or not the following multiplications are defined, and if they are, find the resulting matrix. So as I say again, it's just testing that the number of columns in the first matrix is equal to number of rows in the second one. And once that is true, then it's defined, and then you can go right ahead. Right, so I'll leave you guys to look back and look at that. All right, another set. A plus B, we know how to do that. A times B, we know how to do that. B times A, we know how to do that. A square just means A times A. And then they put minus B. So if you look at that one, A square, you just see there, A times A, you work that out, you get it simplified, and then you minus matrix B, and you're done. So you focus on simplifying this, the multiplication is kind of hard to highlight like that. Let me see if I can use this. Nope, this going to give me, not going to highlight it good either. So you get what I'm saying. This and this, multiply that first, simplify, and then you do the subtraction. So now I have some exercises. It's for the matrices A, B, find 3A, half A, 2B. So that's not new under the sun, right? Not new here. Then it says, find the value of K and the value of X so that this is equal. Now, this is more interesting, right? Because, you know, they mix the concept of having a scalar and the concept of, you know, basically solving for an unknown. So there are quite a few things going on here. Then I have this one, find the values of A, B, C, D. So we are familiar with this type. Already you multiply out with a scalar and then you solve for the unknown. So that one not too bad. Similarly, this one. So given the dimensions of the following matrices, give the dimension of these matrix products. So they just want you to tell them the resulting matrix. I really like this exercise, a good exercise. And then you have more final product of that. So the only one I would probably attempt with you guys now is this one, because I have not seen one so far where the mix, you know, you have an unknown scalar and then they have a other unknown, right? So we can try and map it out and say, hopefully this time I write down exactly what is there. Well, I have to. Some of these questions, if you don't write down exactly what is there, then you're going to be in serious trouble. So we have 0, 1, 2, 0. And then you have plus k, 0, 2, minus 1, 0, equal 0, 7, x 0. All right. So first off, what I would do is to simplify. And for me, simplifying doesn't mean multiplying out this k thing, multiplying out the scalar. So 0, 1, 2, 0. So this now would be, so this is still 0. This is now 2k. This is now minus k, and this is 0. And then this is 0, 7, x 0. Cool. And then we can see what, equality we can work with, right? So we see that 0 plus 0 is 0. So there's nothing interesting there. For this one, it's that 1 plus 2k, 1 plus 2k is equal to 7, right? And then we can do something about this, right? This is just solving a simple equation now. So we can have minus 1 from both sides. I get 2k is equal to 6. And then I divide both sides by 2. You get k equal 3. So we can say k is equal to 3. And we test it 2, 3 is 6. 6 plus 1 is 7. So nothing fancy going on. Now that we have the answer for k, we can use that information and try and get x, right? So we know that 2 plus, and you can put a minus k. So this is this part now, is equal to x. But we know that k is equal to 3. So this is actually 2. And what I'm going to do is just put the minus, right? Since there's no minus, minus, plus thing going on. And just put the 3. Right? And that's essentially it, right? So once you find that, you find x. So therefore, x is equal to minus 1. So you get what k is. K is equal to 3. And x is equal to minus 1. So it looked interesting, but once I follow the concept, it's a regular question, right? Nothing too frightening. All right. And as I said, everything else is like we saw before. Right. So I like how this look. Check this out. So find in terms of A, right? This matrix right here, find in terms of X, this matrix. So things are warming up here. I like this. Even this one too. So we can try which one I should leave. This one may take a little while because you have some extra multiplication. This one, I can try this one with you guys. Let's see. Let us see. All right. So let me carry this over here so I can make use of my second screen. So it says find in terms of x, and it'll give you the matrix, right? You have 3 minus 1, 2, x, and you have x minus 2, 1, 3. Lovely. So Let's work this out. So the same 7 setup that I've been talking about. So and so, not new. So it's okay. 3 times x, which we can call 3x and call it a day, but I'll take my time. And 2 times 1. Then again, so minus 1 times x plus x times 1. Then now we try with this side. So 3 times minus 2 plus 2 times 3, right? So 3 times minus 2 plus 2 times 3. Then we'll go again. So minus 1 times minus 2 plus x times 3. All right. Then we'll simplify. So this is just 3x plus 2. This is just minus x plus x. All right, which we can simplify. This is just minus 6 plus 6, which we can simplify. Easy. And then this is just positive 2 plus 3x. Hopefully we have space. So this is 3x plus 2. This is 0. It looks like a 0. This is 0 as well. And then this is 2 plus 3x. Nice. So that's what we would do that one. Let's bring this back. So this is where we want to get to. This is the bulk of the matter. Right? Let us see. We have ways to go. And what I'll do in good wisdom, I'll actually, what time now? We have time, right?
14.
We have a lot of time. The thing is to do inverse, we do want to overload the thing. So what I'll do, I'll go through, I'll touch on it so that we'll have a good place the next time, hopefully next week. So I'll touch on it. Right? See how far we can go in the time. I don't want to get overly complicated, right? As yet, before you guys appreciate the basics of adding, subtracting, and multiplying matrices. So let me go. So in this section, we will restrict ourselves to square matrices. That is, matrices in which a number of rows equal the number of columns. For example, this is a 2 by 2, this is a 3 by 3, this is a 2 by 2, this is a 1 by 1. Right? We will concentrate on 2 by 2 matrices, examples A and C above. We start by defining the determinant of a 2 by 2 matrix. So this is a new concept now. They're talking about determinant. And all of this is going to come together when you see how we solve for unknowns in a 2 by 2 matrix. You need to get the determinant in order to find something called an inverse. And use that inverse to multiply the matrix itself and find the unknown. So we'll see what we're talking about. So if M is this matrix, its determinant is defined by det M. So that just means determinant. So the determinant of M is AD minus CD. So AB, A times B. So just think of a cross. AD times or AD minus CD. Some people say BC. Don't really matter. You just need to have the cross, right? AD minus CD. Note that is just a number. So for example, examples above. So the determinant of A, so matrix A, would just be 4 times 1, so 4, and then minus 1 minus 2, which would be a positive 2, so you end up with getting 6, right? And then the determinant of C, matrix C, which is here. So this is what 4 times 3, 12, minus 3 times 4, which is also 12, so you get 0, right? Now, they have something important to say when you get 0. For matrix M, this one, if the determinant is equal to 0, we call it singular. And if determinant is not equal to 0, it is non-singular. Hence, matrix A is non-singular and C is singular. And you see that they just tell you, but it plays a very important role when you find in the inverse. So it just building up to eventually show you why that is important, right? So remember, when you have the determinant is equal to 0, that is singular. And when the determinant is not equal to 0, that is non-singular. All right. So work example 1. Matrix, so M is the matrix. So calculate the value of X, which would make M a singular matrix. In other words, that would make the determinant of M equal 0. So all you do is just set the determinant to 0. So you do the cross multiplication and all of these things where you find the determinant was R. Probably I shouldn't say cross multiplication. You just say minus 4 times minus 5, which is 20, and then minus this and that, you get a plus 10x, right? So you get this thing. Set it equal to 0, solve for x. So x is equal to minus 2. So if minus 2 is right here, then this matrix, the determinant of the matrix, right, is 0. That is, matrix M would be singular. Right? Now, bear that singularity, well, I don't want to call it singularity, bear that concept in mind, right? Because it's going to become important. So for a 2 by 2 matrix, we will define its inverse, denoted by M, as the matrix that satisfies xm is equal to mx is equal to I. All right. Now, what does all that mean, right? Here, I is the identity matrix defined 1, 0, 0, 1, and we denote x by m inverse. It is not always possible to find an inverse, as we will see in the following result. And what they will mention or what they're prepping you for is this whole idea of the determinant being equal to 0. If it's 0, then you can't find the inverse, and you'll see why. Theorem, the inverse of matrix M is given by E dot equal 1 over the determinant of M. So if the determinant is 0, then clearly this thing will be undefined. You cannot find the inverse. The other thing to note that I probably should emphasize is that it says here we'll define its inverse denoted by M as a matrix that satisfies this. So the define inverse denoted by M, so here xm is equal to mx. So remember the old thing that we were saying that matrix multiplication is not commutative, right? However, a matrix multiplied by its inverse is commutative. So you can have a matrix and its inverse, but that first matrix is also an inverse of the second one, right? So you have matrix A, so matrix A is an inverse of if matrix A is an inverse of matrix B, then matrix B is an inverse of matrix A, and you multiply them, you get the identity matrix, right? That's why, you know for sure that they are matrix, that they are inverse of each other, because when you multiply them, you get this thing called identity matrix. And we see why that is important. So they come and they say, okay, the inverse of M is given by so and so, and only exists if the determinant of M is not equal to 0. The matrix B minus C A is called the adjoint. Because look, they say the inverse of matrix M. They say original matrix, but the inverse is given by 1 over the determinant of the original matrix. And then you do this thing where you move around the elements and put some minus sign. So where you would have A and D, you switch the places of A and D, and then you put some minus signs on element B and C. So hopefully they have an example that, okay, they have an example down the bottom. So it will become much clearer. And then they come and they try to show the proof. We will show that inverse of matrix M times M is equal I. So this is your M. I'm gonna undo that, guys. So M is A, B, C, D. See there? M is A, B, C, D. And I said the inverse is 1 over the determinant of M. Then you swap A and D. So you put D here, A here, and put minus sign on B and minus sign on C. So that's all they did, right? Put the inverse here, put original matrix here. And then you do the matrix multiplication, right? So it's okay, D times A multiplied by, well, D times A plus B minus B times C. And that's what's going on here. Of course, because of the minus, it is a minus instead of plus. And they go through. Now, this is not important in terms of learning the proof, but understanding how it works is important, right? How do you get the understanding of how it works when you do questions? So work example 2, find the inverse of this. So based on what they tell us, and they say, and show that this is the case. So the inverse, if you look up top, is given by, see it here now, 1 over the determinant of the matrix is swap the switch places of the leading diagonal. I think this one I call leading diagonal, this one. And then put a minus sign on the other diagonal, right? So let's check it out. So the determinant we know is this times this, so 5 times 2 is 10, then minus 3 times 3. So 10 minus 9, you get 1, and then 1 over 1 is 1, right? See there? So you get 5 times 2, that, 10 minus 9 is 1. So A is non-singular, that is, the determinant is not equal to 0. And of course, 1 over 1 is 1. See there, 1 over 1 is 1. And then this whole swapper do right here. So you would have had 5 before and then 2 here. See there? 5 was here, 2, you just swap it. Put 2 on 5, and then put a minus sign on the other diagonal. See there? Minus, you put minus sign on 3, minus sign on the other 3. And just like that, this now resulting matrix is the inverse. So this is the inverse. This is the inverse of this matrix. So all you need to do is just apply. See there, A times the inverse of A, you get the identity matrix 1, 0, 0, 1. If you switch places, they get the same result. The whole idea of them being commutative, right? Now, ultimately, this is what you're trying to get to. You want to use this concept now to solve simultaneous equations. So it says that, so for example, you have the simultaneous equation. 5x plus 3y equal 4. 3x plus 2y equal 2. This can be written as 5, 3, 3, 2. So what's in A is really just what they call the coefficients of the variables. It just means the numbers that multiply the variables. So you just put all the numbers in one matrix, 5, 3, 3, 2, 5, 3, 3, 2. You put the variables in another matrix. So this now is a column matrix, xy, because it's two variables, x and y. And you put the result in another column matrix, 4 and 2. So just like that, see there, ax column matrix A, 5, 3, 3, 2, which is the coefficients. And then matrix X have the variables X, Y. And then lastly, matrix B have the result 4, 2. So what you need to do here, we need to find the inverse of matrix A. Because by finding, all right, is it just like when we have, try and get a good example for you guys. So this is a very, we don't call it now, a oversimplified way of explaining, but we'll use it. We'll take it, right? So we have, say, when you have 2x is equal to, say, 6. And then we say, all right, we want to solve for x. So we divide both sides by 2. We get x is equal to 3. Essentially, that's what the inverse is doing. You have a matrix, right? So this is a matrix with the coefficients. Then you have another matrix. This is a matrix with the variables. Then you have another matrix equal, this is the column, another column because the x is a column matrix. You have another matrix, call it B, that has the answers, right? That has what the equations are equal to. You're trying to solve for x. So in order to get rid of A, you apply the inverse. And in this case, above we would just divide both sides by A and say, okay, this divided by this, and so on and so forth. This cancel and we'll find what x is. It's like a similar thing, but you're not dividing like this. This is not how you get rid of the A. You get rid of the A by applying the inverse. So if you come so, right? And then, all right, let me do it in the next row. If you come so this is the original thing. My bad. It's supposed to be x. And then you have, say, apply the inverse. And then apply the inverse again. No, what happens is that this gone. The A inverse and the A gone, and you just get x equal A inverse B. And you multiply these two matrices, and you get the result. And that result would be the unknowns, right? So you're solving for the unknowns of x and y, where they intersect. Because remember, simultaneous equation, you have a line that goes so, you have a line that goes so, and you try to find where they intersect. All right. So let us go back. So see there, multiply the inverse, see there, and it's to the left, and this is also to the left. Right, so that is very important. Don't think you can put this A inverse over the other side to the right. And to be frank, I would have to test it, but I know you should apply it to the same side, to the left. Yeah. Come to think of it, it needs to be to the left. Let me show you why. Because some people make the mistake, Let me show you. All right. To the left, to the left. So this in the example that we're looking at, this is a 2 by 2 matrix. So you have a 2 by 2 matrix. B, so A, let me call A inverse is a 2 by 2 matrix. B is a 2 by 1 matrix. Now, why it needs to be, apart from the fact that you apply this to the left and you should apply this to the left of B, it has to be to the left of B simply because in order for it to even multiply, the number of columns in A inverse must be equal to the number of rows in B, right? So that's why this is valid. But if you go make the mistake and go do B A inverse, then you're trying to multiply a 2 by 1 matrix with a 2 by 2 matrix. And this is not valid because the number of columns in B is not equal to the number of rows in A. So this could never work, right? So come back to the concept again of, I call it compatibility. Then I think they not refer to it as it being defined, right? So you have to remember these things because people run in and they think they can multiply anyway and stuff. So that's why practice is important. All right. So they come now and say, all right, that. See there, you multiply the inverse to both sides and you end up here, which is just you now needing to multiply these out to get what? Get the solution for x and y. Right? And of course, check the solution. So this is, you don't have to do this. This is not what, this is just for teaching purposes, right? They're just showing you that it works. Worked example 3. So they have this one. Given that m is equal to 2, 5, 7, 15, show that m is non-singular. Write down the inverse of m. Write down the 2 by 2 matrix, which is equal to the product of m times m inverse. Pre-multiply both sides of the following matrix equation by m inverse, hence solve for x and y. All right, so even though the solution is there, you know what? Let us go through it together here. Maybe I can do one that is not on the, that is where the solution is not given. All right. So we have the determinant of m. Remember, we just multiply 2 times 15. So let's multiply the diagonals and minus them. 2 times 15, 35, 7 is 35. 30 minus 35, I get minus 5. So it's this one, this diagonal, minus this diagonal, the product of that diagonal, right? So this diagonal, product of this diagonal, minus product of this diagonal, get your answer. The determinant is not equal to 0. So that means it's non-singular. So you can go right ahead. If this is 0, there's no way of finding the inverse. So stop. You look and say if you do anything wrong. If you do anything wrong, then you can't go any further. You can't find the inverse of a singular matrix, right? Then now you find the inverse, which is 1 over the determinant times the adjoint of m. And the adjoint of m is just where you switch places of the top left and the bottom right elements, switch places, 15 turn 2, and then put minus signs on the other diagonal, the top right and the bottom left, put minus signs on it, and multiply by 1 over the determinant. And that is the inverse. And of course, this 1 over the minus 5 is like a scalar. So you just multiply it throughout. You get, so 1 over minus 5, you get minus 3. This is 1. This is 7 over 5 because minus minus. You get a positive 7 over 5. And you get minus 2 over 5. Right? And we know that m times minus m times the inverse of m equal I, and I is just 1001. Here, in order to find what x and y is, you pre-multiply to the left, both sides to the left, m inverse, and then you're tasked with to find this here. So you're going to highlight everything, but that's not what intent is, just for this. Hold a moment. Let me plug in charger. So yeah. So m inverse times minus 317. You work that out and you get 26 over minus 11. And this is the answer that you're looking for. So here is a determine which of these matrices are singular, which are non-singular. For those that are non-singular, find the inverse. And we have an idea of how that is done. Find the value of A for which these matrices are singular. We did a question like that before. Now, I'm seeing something that looks interesting. This one. This one looks very interesting, right? It looks too interesting though. Let us see if we can actually do it. Putting myself under some pressure, right? Let's see. It's a final value of A for which these matrices are singular. Let us see. So we attempt this one. That's the thing, guys. Let me show you something. You come and answer some question. You probably look on that one and say, yeah, the one I can do. And then you just don't bother to decide this. No, man. I feel look on the one will look most challenging and give it a shot. Right? So we can even do this first now, but we have to do this one. This look like a healthy question, right? Hopefully it doesn't disappoint, right? So the new slide. So the question asks, find the value of A for which these matrices are singular. And we know it's a singular mean it's equal to 0, right? Where the determinant is equal to 0. The determinant of the matrix is equal to 0, and that is the definition of our matrix being singular. So the first one is A, 1 plus A, 3, 2. So I have 4 elements. So this element, the 1 plus A together is like an element, 3 and 2. So the determinant is this times this minus this times this. So A times 2 minus 3 times this one. And this should be equal to 0 for it to be single. So we're trying to find values of A. So this is 2A. And we'll just multiply this, right? This is 3 minus 3 equal to 0. So when I get somewhere there, in this, if we group up with the A's, then you get a minus A. And you get a minus 3, right? And all you're trying to do now is to solve for A, right? So minus A is equal to 3. That is, A is equal to minus 3, just like that, we did that one. So when A is equal to minus 3, this thing is singular. So go to the more interesting one. So this is A, right? So make sure. All right. So the determinant of this matrix is multiplied by this one And then we'll have this multiplied by this. And this is supposed to equal to 0. So what can we do? Right? This looks very interesting. The first thing I would consider doing is you have to see how you can move them, but everything is they're in brackets now, right? So the I guess if we call them terms meaning brackets not going to help you to get to anything. So you have to try and see how you can simplify something somewhere. Now, this reminds me of this piece, and we multiply it all, but I can say these. So these are factors of this, the difference of two squares, right? So already I see how this can simplify. But I will show you what. 1 times 1 is 1. 1 times minus a minus a. A times 1 is a. A times minus a squared. So probably should write it bigger, right? Over this side, we're going to put the minus sign. We'll ignore the minus sign for now. All right, I'm going to put probably not a square bracket, a round bracket should be fine. So I'm going to leave this minus sign on the outside. So a times 3 is 3a. A times minus a is minus a squared. 2 times 3. See, I'll do it like this and this, right? Now reach here. 2 times 3 is 6. 2 times minus a is minus 2a. All this equals 0. So we're going to try and simplify now. So know that this p is gone, right? That cancels. So this is just 1 minus a squared. Then what else can we do? Within this, I'm not even going to multiply the brackets yet with the minus. I want to simplify in here first. So it's at 3a minus 2a. So we can write this as just a minus a squared plus 6 equals 0. Now I'm going to multiply the brackets. Multiply the bracket with the minus. So this is minus a plus a squared minus 6 equals 0. Lovely. Because this guy is gone, right? So this is gone. Let me see if I can use a highlighter. This and this gone. Then that makes things very simple now. So I have 1 minus a minus 6 equals 0. Right? And better yet, in this line, let me even simplify the numbers, right? The constants. So 1 minus 6 is minus 5. So I have minus 5 minus a is equal to 0. Minus a is equal to 5. A is equal to minus 5. Just like that. So when a is equal to minus 5, the matrix here will be singular. That is, the determinant is equal to 0.
Sir.
Yeah?
So what to do with the 3 in the bracket here, the 3a? You didn't do anything with this 3.
Of course. 3,
Where?
3a minus 2a is a. 3a minus 2a is a.
Oh, I didn't see this 2a. Okay.
All right, great. So everything else makes sense to you?
Yes, sir.
Okay, great. All right, so we'll move back now to this. All right, so we did that. So you guys can try this one and see, right? When you have some time. But when you have some time in time for next class, hopefully early next week.
Okay.
It says now, given that AB is equal to C, find an expression for B. That's kind of weird. What do you mean? Given that AB equals C, find an expression for B. If that mean that I should apply the inverse to both sides and I have B equal A inverse C, then fine, I can do that, right? Then it's a find B when A is equal to this and C is equal to that. Cool. So just as I anticipated, so I just want you to just find the inverse of A, and that will give you the answer for B. No problem. So I can probably try that question. Let me see what else is here. All right, so given that, all right, so hopefully I can do this question now. And then hopefully one of these I'll call it a day. If not, just do this one, because there are examples of these up top. So let us begin. Slide. So this will require some serious concentration. Whenever I see matrices questions, I just know it will require concentration, right? So let's say, not that questions are required, just that you require a little more. Given that AB equals C, it's a final expression for B. So right, so not a typical question. So all I did was to say, okay, B is just A inverse C. And I call it a day. Then the next one says find B. Well, let me back. Find B when A is 2 minus 1, 4, 3. And C is 3, 6, 1, 22. I don't know why I put that big 22 in there, but their question, right? They should know how it's simplified nicely and whatever. So in order to do this question, I need to find A inverse so that I can pre-multiply both sides by A inverse. Now that's what I got this here, you know. Let me just make a little jotting down here and then rip it off. So AB equals C. To find B, I just put my A inverse, so pre-multiply to the left, right? So A inverse both sides, see there, both sides. So this now, the A's them cancel, I get identity matrix, right? So I count about I and then B equal, but nobody writes I, you know, that's a nobody writes. It is like 1A. You don't write the one, you just put A. So this is now B, right? So that's essentially what we want to do. We want to find A inverse so we can multiply both sides to the left and know that A times A inverse going to give us the identity matrix. So we're not going to even work that out because we know what that result is. But we know we're going to have to work out A inverse multiplied by C, because that's how we're going to get the answer. Right? So let me just undo all of that. Probably easier to erase. Let me switch on fast now. All right. So let us see now. So to find A inverse, remember, we got something before that says 1 over the determinant of A multiplied by the um, adjoint of A. So we need to find the determinant. The determinant of A is just you multiplying, subtracting the product of the diagonal, this diagonal like that. So 2 times 3 minus, suppose we are um, minus 1 times 4, which is just 6 minus minus is positive, right? So this may work out to be a plus 4, which is 10. Right? So we have 10. All right, so that's one known. We need now to find the adjoint. Draw a bit of dividing line. So the adjoint of A is just to switch the places of the leading diagonal element. So put 3 here and put 2 here. And then you put a minus sign on these, right? So because I have a minus sign already, when you apply a minus sign again, it will become a positive. And then this now a minus 4. Right? And then to wrap up is just to put 1 over. So the A inverse is just, let me see if I can fix this. Right, never remove it. So A inverse is just 1 over 10 multiplied by 3, 1 minus 4, 2. See there? 3, 1 minus 4, 2. So I have adjoint, which is just you switch your places. This becomes 3, this is 2, and then apply minus signs to both of these because that one already become positive, then minus that. The adjoint, so 2 times 3 is 6, and then 4 times, say minus 4 times minus 1, which is, so that'd be minus 4, and then minus minus make a positive, that's why you get 10. The inverse is 1 over the determinant, 1 over 10 multiplied by the adjoint. So what you can do next is to then multiply the scalar. So you have 3 over 10, 1 over 10, minus 4 over 10, 2 over 10. Right. So this is going to be interesting, right? So we have to concentrate a whole lot. All right. So let me see now. So we have, hopefully we can see a piece here. I think I see a piece. So A inverse, 3 over 10, minus 4 over 10, 1 over 10, 2 over 10. All right. So what we're supposed to do next, going back to this slide, is to multiply this inverse by C. And C is that over there, right? So let me even just go to it and save some time. I'm just rub that out and put A inverse times C and just save some time and put C right here. So this is our A inverse and C is I think 3, yeah, 6, 1, and 22. So I have some serious multiplication to do. All right. So this multiplied by this. So after that, let us see. So I have 3 over 10 times 3 plus 1 over 10 times 1. So luckily the numbers not too tough to do, right? The don't set up so far. This times that. So I have a minus 4 over 10. Of course, it's going to be simplified, but we're going to leave it like this for now. So minus 4 over 10 times 3 plus 2 over 10 times 1. Next up, we're going to do the other column over here, right? So let me show you. So it's going to be this times this. So this is 3 over 10 times 6 plus 1 over 10 times 22. So again, this times this. Minus 4 over 10 times 6 plus 2 over 10 times 20. All right, so this is 9 over 10 plus, all right, let me work it out piece by piece, no problem. 9 over 10 plus 1 over 10. This is what? Minus 12 over 10 plus 2 over 10. So make this big. Then this now is, make this a little better. All right, over here now we have 3 over 10 times 6, so that's what? We have 18 over 10 plus 22 over 10. And then we have minus 24 over 10 plus 44 over 10. Now I can simplify a little more. So 9 over 10 plus 1 over 10, that's 10 over 10, which is 1, right? Let me even leave that simplification for another. I doubt I'll have space, but I'll leave the simplification for one more step. So this now, negative 12 over 10 plus 2 over 10, that's 10 over 10, right? So I have at least negative 10 over 10 to be accurate, right? What about this? 18 plus 22, that's 40. So I have 40 over 10. And here now, minus 24 plus 44. Because remember, now, all of them have the same denominator. That's why I avoided canceling too early. Because I do, trust me, I don't want in and out fraction gymnastics. I try to work out, you know, all of that with different denominators, finding LCM, and no. You try and hold on to this denominator as long as I can until you reach a stage where it's nice and comfortable to reduce the fractions, right? So right here, minus 24 plus 44, that is 20. So 20 over 10. Look at that. All right, that no draw sentence. So initially I was concerned about these big numbers, but when I do the thing properly, they make sure that it's simplifying nicely. Of 10 times. Like 9 out of 10 times, you think it's supposed to simplify nicely. So what you're 10 over 10, I can make this even smaller now. This is just 1 here. This is 4 over 10 is just 4. Minus 10 over 10 is just minus 1. 20 over 10 is just 2. So at the end of the day, that's what I get for the answer. A nice, clean, as I said, it's not always clean, but it feels good when you get something that results like that. I'm saying it's not all the time, but yeah. So we get the concept, right? And we get the concept just in time because class finished now, right? So I would say, so I put this in a group. You guys attempt this on your own. These on your own. I will talk about it next class. But the good thing is that I think we have done the bulk of matrices. This now is just some transformations thing, right? But we've done the bulk. So it's just a practice questions now. So until next time, take care, walk good.
Okay, sir. Thank you.
Yeah.